x squared has a positive coefficient in front of it, and the transverse axis, or the the main axis there is the x-axis. It doesn't have to be A. A is just what the larger one is, but because the asymptotes can change, even though it could be along another axis, the asymptotes can change. And we're just looking at a few examples, but maybe we'll come out to the examples and we'll kind of talk about it. Anything else other than 3 over here? Okay, so let's take a look at number 3. And this is given as 4x squared minus y squared is equal to 4. What we're going to do is we want to get that 1 on the right-hand side, so I'll divide everything here by 4. So I end up with x squared minus, and I have my y squared over 4 is equal to 1. Put that over 1 so you can kind of think of this, what's happening here. So if I'm looking at this, it's the x squared, so I know my transverse axis is along the x, so it's going to open this way. And again, for this, essentially this sort of problem here, we're saying that our A is just whatever is with the x term. So it's not necessarily the largest one. So I have my A squared is equal to 1, and B squared is equal to 4, so that tells me A is 1 and B is 2. So A is not necessarily the largest one, but in this case, it just has to be whatever goes underneath the term that doesn't have the negative in it, because the transverse axis is this way. Okay. The other thing we're going to have is we have c squared is equal to a squared plus, b squared. So that's equal to 4 and 1 is 5. So c is the square root of 5. So what can we do? Well, we can set up a little set of boxes over here. So let's take my b along the y, so it goes up 1, 2, 1, 2. 1, 2, and 1, 2. Now, this creates a little box that's kind of like A along the X and then B along the Y, if you will. So it's my axes here are, in this case, for the transverse, my asymptotes, I should say. I'll write them here, the asymptotes. Y is equal to plus or minus B over A. So it's equal to plus or minus AX, plus or minus 2X. And I take that creates a little box over here. So if I go up 2 along the Y and 1 over in the X, I take that down 2 and then over 1, I'm going to create this little box over here. Not perfectly there, it's drawn there, but it's squeezable. This will create a couple of asymptotes that my graph will get closer and closer to. If I go from corner to corner, I get these asymptotes. It should pass through the origin. It's a little off, but it's okay. This is the general idea over here. Something like this. And this should go through the origin, but it's not. So I'm off a little bit there, but that's okay. Okay. Continuing on, we know that this is my transverse axis. So the X is transverse. So this is where I'm going to place my, if you will, my foci. So it's the square root of 5, which is just a little bit over 2. That's right about there. So it's equal to plus the square root of 5, 0, a little bit over 2 over here, which is minus the square root of 5, 0. Those are the foci. And it's going to kind of come through this way. And it's going to pass through my vertex over here is at this location right here. So this is my minus 1, 0, and plus 1, 0. So if I were to draw the graph of this curve, it has two different parts. So this is my, if you will, those are my two vertices. And what it's going to do is it's going to be about this foci. So it's going to look something, let me get closer to that, something like this. It's going to get close. And over here, it's going to look something like this. Oops. Should get closer and closer as we go there. Those are the foci that are kind of, working at the distance between points on that line and the other one on the other side. And these lines here, these asymptotes, this is, y is 2x. And in this case, y is negative 2x. Those are the asymptotes. And they're created by this little rectangular box to kind of help guide you. And you can see the A goes with the X in this case because it's the transverse axis, and the B goes with the Y. So it is not true that, A has to be for the larger one like it was for the ellipse. The ellipse is different than the hyperbola. It's whatever is under the term without the square, that becomes the A, and then the other one becomes the B. Now, when you flip it around over here and, you put the y squared first, well, then this is a main axis, a transverse axis. It's going to go this direction here. And then instead of plus or minus b over a, it's plus or minus a over b, because it just switches around the way everything is set up over here. Because the a goes with the y and the b goes with the x now, because the y has a positive in front of it. The y squared has a positive in front of it, but the x squared has a negative in front of it. And that's it. That's everything we need to know about that, but the ABCs of hyperbolas. And again, if we want to, we can also take a look at, I think I have a copy over here of Desmos as well. Make sure I did it correctly, didn't kind of rush into something. And it's just nice, allowing you to kind of use this on the test. So we have 4x squared minus y squared equal to 4. And there it is. Same little graph that I'm showing there. Let's put the asymptotes. Y equal to 2x and y equal to a negative 2x. And there you go. You can kind of see those are the asymptotes. And you have a box over here that would define this from here to here. It goes from here to there. Here we can put that in. So you have x equal to minus 1, x equal to 1, y equal to 2, and y equal to minus 2. And you can kind of see that box that I put over here that my asymptotes go through. Kind of a little bit busy, but I can't just stop it. I probably can. I can just have it go up for a certain y and create this little box over here. But what I could do is just at least make them a little less cumbersome over here. And I could also do my asymptotes if I wanted to as well to make them different. So there they are. There's that little box I'm talking about. And here's the main function over here. Let's change the color of that, like that. Black. Let me change the pixels there. But anyway, okay. Oops. Go back. Now, there we go. But same sort of thing. I'm showing the asymptotes. There's the actual curve itself. And there's that little rectangular box I'm talking about. That helps guide me in terms of how do I draw those, what we call these slants. Sometimes they're called oblique asymptotes. So that's everything you need to know about an hyperbola. So anything else? Anything about
We'll do number 4.
What's that?
Number 4.
Number 4. And what's nice is you can plug this right into an application like Desmos and get a quick visual confirmation of what you're looking at. See that it does agree with what I sketched out. Number 4 looks like 3y squared minus x squared is equal to 27. So what we're going to do is we're going to get a 1 over there, so we're going to divide everything here by 27. What do I have? I get y squared over 9 minus x squared over 27 is equal to 1. Now, in this case over here, this is my transverse axis. It's the positive it goes, so it's going to be just the opposite of the way we have the other one. Okay, so a squared is 9, or that tells me a is 3. B squared is 27. That tells me b is equal to 3 times the square root of 3. I can just write this, bring out the 9, and then have that. So they're similar in that. So my c squared is equal to 27 plus 9 squared, which is 36. So in this case, c is just 6. And it's going to go to the transverse axis over here. So what I do know is it's going to go up to, in this case, we have it for the y, it's going to take us up to 3, and the x is going to take us a little bit further. Do that in blue. So here are my vertices. I go, 1, 2, 3, there's my vertice, and then 1, 2, minus 3. Okay. I can also put my foci over here, 4, 5, 6. There. Now, when I do when it's the y is the transverse axis, my asymptotes, there, y is equal to plus or minus a over b. It flips. Okay, times x, excuse me. So in this case, y is equal to plus or minus 3 over 3 square roots of 3 times x, so that will cancel out. I could write it if I wanted to. Y is 1 over the square root of x, or I could write it as plus or minus the square root of 3 over 3x. Many different ways of writing that, which is equivalent to 1 over the square root of 3. But then I also kind of put the boxes over here. So in this case here, that's 3. So my box is going to go a different color this way. And this goes out, the other one goes out to 3 square roots of 3. Let's get an estimate of what that looks like. So 3 times square root of 3. Think about 5.2. So 1, 2, 3, 4, 5.2. 2, 3, 4, 5.2. Okay, so that's what it looks like. Now I can draw my, if you would like, different color here, my lines to guide me for my asymptotes here. Kind of go this way and that way. And the same thing over here, roughly right there. Something like that. Now, if I was going to fill this in, it's going to go this way. So what it's going to look like is something like this. And based upon those things as well. So this distance over here, as you can see, is little, it's not a point on the graph, but it's a point over here. This is nothing more than my x is 3, square root of 3, 0. And this little point over here to find my box is minus 3, square root of 3, 0. And the blue line is my graph right there. And again, I can go and use my Desmos just to make sure I didn't mess something up. With a quick sanity check over here. Let me get rid of all these. And I can put the same thing, 3y squared minus x squared is equal to 27. So you can see where it's going through the 3 over here. Now I can put the other things I have over here. I can do y equal to, let's do plus x over the square root of 3. I can write it that way. X divided by square root of 3. And the next one over here, y equal to minus x divided by square root of 3. And there are my boxes. I could put, again, I do the same sort of thing if I wanted to. Y equal to 3, y equal to a negative 3, x equal to 3 square roots of 3, and x equal to minus 3 square roots of 3. So you can see where this box goes right through my asymptotes there, just as I've drawn it on the board there as well. I want to see those, just kind of make those go in little dash lines if I wanted to. Well, this one I'll make this go into a different line. And this and this. Now my asymptotes will be dashed and all the other boxes will be little dots. So there's a graph of my line. Let's make that black. And there we go. So those are my two asymptotes. There's a little rectangular box I'm creating, which is different than, you know, the asymptotes. But notice the asymptotes go right through the corners and right through the origin. But now notice instead of B over A, it's A over B. So unlike your ellipse where A is always the largest, the A is whatever goes under the positive square term, and then the B is the other one. And C is always, I sum the two squares together and I get my C is the square root of the sum of those two squares. But that's it.
Excuse me, Professor.
Yes,
I just
question.
have one quick question.
Mhm.
So, is it true that whenever A is larger than B, that the parabolas will be going through the y-axis, and then whenever B is larger than A, they'll be going through the x, or is that not always
No,
so?
the thing is, I can say, it's notice there's a positive in front of the y squared, with this being positive over here. The right hand side has to be positive. If it's positive over here for the y squared and negative for the x squared, then the y-axis is going to be the transverse axis. If it switched around and this was negative and that was positive, then the transverse axis would be this way. And A over B would switch to B over A for that. I just show that on here. It's a simple change in the sign of everything over here. In fact, I could just change the sign of the right-hand side and show you this. So all I need to do is change the sign of this right-hand side, and that's just changes the sign of both X and Y, and it flips the other direction. But notice now it went to, kind of flipped everything over here, because now my A is equal to the, essentially 3 square roots of 3, and my B is now 9 because it's switched over here. Changing that sign means both of those flip signs.
Initiating moisture.
But now, since I switched my A over B, to get it back, I have to switch it back to B over A. Because now, whereas A was the coefficient under the y squared in the last one, it's now coefficient under the x squared term.
Scientist Jackson Clark.
So it kind of flips everything around.
It's nice to be let out of
So
the cage
it's
every now and
not
then,
dependent
especially
upon
when new hardware
whether A is larger than B. It depends upon which of these has a positive coefficient when your right-hand side
I don't know what
is
you would call it.
positive.
A console, I
same thing as if I
suppose,
made this
is the right word to use for it.
positive.
I think that's what it's labeled, yeah.
So what you're looking at
Same
right
exact
now is
feedback.
basically footage I shot since I'm the one unboxing
I don't know if that
the console.
clarifies it for here.
What
It's
you
not
get from this is
like
a
for
pretty standard, I would
ellipses,
say,
yes. A
big
squared,
black
whichever
kind
was
of
bigger
box.
was important.
It's very
Here,
boxy
it's
in
where
appearance,
does the
Charlie. I
negative
don't know if
sign
that's an
go?
issue with you or not. I don't
Well,
personally have an issue with it.
It's the negative sign in
Yeah,
front
I
of
think the
X
design's
squared term,
actually
then
pretty
it's
nice.
the
It's
Y
like some
term,
postmodern
axis is
deco, maybe a
transverse.
bit
The
gothic
negative
in
sign
there,
in front of the Y
inspiration, I
squared,
would
then the
argue.
X
And
axis.
the thing is, Jackson got his
We had
at an
originally-
early time, so he got to spend a lot more time with it than I have. I went
But
on a
you do have
trip,
to flip
on a hiking
these,
trip to reconnect
otherwise,
with nature, to
the
realign
boxes
my
would change.
chakras
Because
before
you're
coming
swapping
back
the
to
X and
spend
Y,
time
so
with
you
the
have to kind of
Xbox. So
Flip
Jackson's
the
definitely
X and
going
Ys
to
over
be the
here.
one
That's
really.
equivalent to swapping, because for the one, the Y, the A went under the Y term, and then if you flip it to this axis, the A is going to be under the X, so you got to make them equivalent. You notice we have the same box there. On both of them, they had the same exact box. The only way to do that is because I'm changing A and B. I'm flipping the A and the B to make that work. I have to use Y is equal to plus or minus B over A when I go this way. Otherwise, if I left it like this, the box would go this way and narrow, and it wouldn't match up. So it's just, essentially, you're swapping the A's and the B's when you go from the transverse being the x-axis to the transverse being the y-axis. A and B is a swapping. The C value stays the same, but depending upon, is it plotted on the y-axis or the x-axis? So those are the two cases. So does that help at all? So those are hyperbolas. Something very basic that you should be able to draw. And when you draw, so I'd like to see the sketches of these rectangles. And you can see it does work out very precisely when I did it in Desmos to what my qualitative sketch looks like here. And here's the two foci. That's what you don't get in Desmos. They don't show you the foci. Okay, so that's essentially everything you ever wanted to know about hyperbolas. The last thing has to do with the classification theorem. And this should look familiar. And it's part of the quadratic formula. It is related to that, but it can also be used to classify the different types of quadratics. Because we have two variables, x and y, and they can be squared. So you can have a general form of a quadratic expression in two variables. It can look like, a x squared plus b times xy plus c y squared plus dx plus ey plus f, where the capital alphabetical letters are all numbers. They're just real numbers. And this could represent, could represent a parabola. It could represent an ellipse, or even a circle, if we kind of consider a circle a special ellipse. Could represent hyperbola, or it could represent nothing. And we're not going to be considering that too much. That's a degenerate case. It might just be a point. It could represent nothing. This doesn't give you anything. And that's the degenerate case. And it turns out that the D, E, and F, so D, E, and F, the only thing they do, they don't impact the type of conic section it is. They just move it around the XY planes. These just move the center point. They move the center point. So just shift it around. Right now, we've been doing everything centered at the origin. So notice we didn't have any X or Y's there, etc. That's all they will do. This is what captures what's going to be the shape. Now, turns out that you can have x squares, y squares, and both x squared and y squared, and it's a parabola. We're not used to that. We're just having a y term over here, and then the other terms vanish. Either the x squared vanishes, or the x term and the y x squared vanishes, something of that nature. But a parabola can open upward, downward. It can also open at an angle. And that's what this can do. This can kind of rotate. This B will rotate whatever conic section you have. That's the role of B over here. A and C is kind of stretching along the X and Y axis, but B will rotate whatever conic section you have. So in hyperbolas, which kind of go like this or like that, you can have a rotated hyperbola that kind of goes like this. Which this would be my transverse axis there. And there's a simple relationship, and I kind of showed you in the textbook how it's related. It's a complicated thing, but the classification theorem says the following. If b squared minus 4ac is equal to 0, it's a parabola. You could still have, y squared and x squared terms there. If, however, b squared minus 4ac is negative, it's an ellipse. And then if b squared minus 4ac is greater than 0, it's a hyperbola. That's how you classify. Just take a look at whatever those numbers are. Now, one of the reasons I like to show this is not so much that you're going to use this in calculus, but this is the same way of classifying. Some of you may have heard of differential equations. I'm teaching a course on ordinary differential equations next semester. That's after you finish Should have finished all 3 semesters of calculus, because sometimes people take it as a calculus too. But when you go beyond those and go to something called partial differential equations, this is further in the calculus, differential equations. You use the same classification scheme. You have parabolic ones, elliptical ones, and hyperbolic ones. This is the kind of like the heat equation. This over here is the wave equation that you get in partial derivative. And this is kind of like, it's kind of like your elasticity equation. How physical things can get deformed and they under stress. And you classify partial differential equations via the same technique. But instead of having x squared, y squared, you have derivatives over there. And it follows the same sort of classification. So it's interesting that we see these common themes cropping up throughout. Because remember where we got this from. Remember where this comes from. You have my ax squared plus bx plus c equal to 0. And you want the solutions. X is equal to a negative of b plus or minus the square root of b squared minus 4ac over 2a. Everything hinges upon what's happening under that square root. Same thing happens here. It's the same exact phenomenon that's going on. So you have it here in basic one single variable algebra, crops up over here in 2 variable algebra, and it will kind of crop up again much later on when you're dealing with these things called partial differential equations, which is well beyond the calculus. But it just happens all the time. Now, if you're in a engineering or scientific discipline, you will see these before you finish out your, you'll see them in your junior year. And at the latest, some of you, if you do some certain sciences, you may not see it too much until your senior year or even the first year of graduate school. It depends. But that's the only reason I like it. So this one's relatively easy. Put the numbers in, you get 0, it's a parabola. Even though it may not, the equation you're looking for may not look like a parabola, it turns out it is. Because it may have both, x squares and y squares going on. I say, well, I can't. If it's x squared and y squared, doesn't, how can it be a parabola? It's because it's a parabola who's been rotated. It's not up or down. It's either going this way or it could go the opposite way, depending on the signs of those numbers. And that's all it is. So if this is true, parabola. If it's negative, that means you have a square root of a negative quantity. It's an imaginary number. Remember, imaginary numbers are kind of associated with circular things. They're e to the I theta. So it kind of works out there. If it's not, but it's a real number over here, that's where you're getting no longer that circular, not that connected ellipse or connected circle. You are instead getting these hyperbolas. And they could be up and down, right, left, or at any angle. If B is there, it's going to rotate whatever conic section there is around that thing, and these will shift it around the XY plane. So it can get very complicated. And that's all that is. But this one isn't that hard. Just plug in the numbers and figure out what you got. It doesn't matter if you put the a with the x squared or and the c. You can swap these. It's not going to change the results. But b is always the xy term. So if I happen to call ca or ac, doesn't matter. The big thing is b has to go first. And that's all. And you ignore all those. Because again, they're just going to move the center point around. Or they could, and I'm not going to get into that at all, it could be such that it's an impossible thing. It gives you a degenerate case. Doesn't work out. And maybe just only one point on the entire graph. So as an idea, let's just kind of show you maybe what we mean by that. Let's take a look at something. Let's see, where is that? Let's take a look at the graph of number 1. It's classified, if you plug everything in, it's classified as a parabola. So if I put problem 1 in there, so I get 4x squared plus 4xy plus y squared plus 3x equals 0. That happens to be a parabola. Even though I got both x squares and y squares, I have here a parabola. It's no longer centered at the origin. It's no longer straight up. It's at an angle. So it's kind of going off in this other angle here. This is center, over here. It's not there. That's not the center of it. There's some line over here. We could figure out what that angle is if we wanted to. And then you can see if I put, say, minus y, what does it do? It just will start and put minus, let's do 6y. And you see it moves it around. Minus 4. So these numbers here, they don't change it from being a parabola. What they do, however, do is change it from its location being located at the origin. Now, if I got rid of this altogether, then you kind of go your degenerate case going right through. So in this case, it's a degenerate case right through the origin now. But if I added a little something over here, such as 5, then it starts to create this. I can show it over here. Get strange degenerate cases. Let's see, we'll take that to minus 5. The minus 5 wouldn't give me anything. So you can play around with these things and kind of see what is happening. There's my original problem over here. Now, if I suddenly change this to, say, a negative, there it is. I got a rotated hyperbola. I change this to a positive 3. There it is. I got a rotated ellipse. So just by changing these coefficients, I get different types of conic sections. And they're rotated, and their origin is no longer, they're not shifted at the origin, if you will. So you just have to be careful with that. That's all it is. That should be relatively simple and easy. Any questions on these? These are conic sections. They can be fun. We don't use them as much in analysis in the calculus as they were in the older days. A good way of looking at different things, but now we use other techniques. But you should be aware of them. And that's what this is. That's why I didn't put an elaborate presentation here at the end. Sometimes, in certain cases in MAT 125, you might spend a couple of weeks on these things and get into the minutia and start seeing, let's move it away from the center and stuff. I just said, let me just give you the basic ones and just go from there. And I did want to show the classification theorem because it is representative of something you've seen throughout. Basic single variable algebra, now 2 variable algebra. Then you can go to, 3 or 4 variable, in this case, calculus.
I had a question.
Yes.
Can the values of A, B, or C, can they be a negative?
Well, yeah, they can be negatives, and they will be, and that will change this. This could change this to making this a positive, so it's greater than its hyperbolic. They can be any sign. You will, as you saw by playing there, you might end up with a degenerate case. So we're not going to be filtering out for the degenerate case. We're just looking for these by just looking at essentially the first 3 parameters. But it has to be something that the right-hand side will agree with. For example, let's put a simple idea of a degenerate case. Say I had x squared plus y squared is equal to a negative 5. That's impossible. I can't add 2 squares together and get a negative. It doesn't work. That would be an example of the degenerate case. So sometimes things do not work out. But in general, we can say, if the numbers here are such that it still makes sense, mathematically. Now, if I put a positive 5, that's going to be a circle of radius the square root of 5. Or if I put, say, 4, that's a circle of radius 2. -4, nothing. There's no, connection here. I can't add 2 positive numbers and get a negative. Positive then becomes a circle of radius 2. That's all it is. But yeah, this A and B, here the sign of B doesn't interact that much because I'm squaring it. So if it's negative, it turns positive. If it's positive, it turns negative. But here, the signs do matter. It'll change the type of conic section I'm dealing with. And like I say, this B, it's a rotating effect. Just by putting an XY term in there, you can take whatever conic section you have and rotate it around. Any other questions? That's it for this course. We don't have anything else to cover. We are done with all the new material. So moving forward, relatively easy. There's no more homework that you have to submit. What I would, suggest that you do for us on, let's see, what if I do? On Monday, we're going to be reviewing. So I'm not checking homework, but for the review, my recommendation is look at the chapter 10, 11, and 12 practice tests. 12 is relatively short. 10 and 11. 11 has a lot of stuff. That's chapter 11 is pretty much the focal point of the calculus. So you really need to be well versed with that. It has all the different properties, the functions, and all the analysis that you do with them. That's why I like to do this and wrap it up at the end, because it's closest to the calculus. This was, we covered a lot of these things. It does duplicate what we did a little bit prior in the semester, but that's okay because this is something that you need to take away when you go into the calculus. All those techniques are important. Because some textbooks are actually called calculus with analytic geometry. And that's where it comes into. The analytic geometry is all here. But it is also based upon all these other analysis techniques that we did early on, as well as the first part of this, which was the important part of what a function is. And this is going to be what takes you effectively into a calculus course. So what we're doing is we're going to review, and then we'll take our test, and then I'll tell you what to expect on the final, the part 2, which is I went with the consensus that it would probably be better to have the last 2 tests give you that first, because that's the stuff that's in your most recent memory. And then we'll do a quick review and go to test 1 and 2 material, or test on chapters 1 all the way up to chapter 7, as opposed to 8 through 12. That's our first part is 1 through 7. The second part over here is chapters 8 through 12. And again, you look at your old tests, or you can also look at the practice tests. Go through them again and see, do you remember how to solve those problems? That's an effective way of doing it. And I'll give you some more feedback on the final there. Then I'll just take these 2 tests and I'll add them together. I don't know if they're each going to be, they each are probably not going to be 50 points. It might be a slight change in there. I have to double check what I'm going to put for that. But they're roughly about 50% each. They may not be exactly, but together they will add up to your final exam grade. It's only going to count as one final exam, just in 2 parts. But any questions? Anything else? Everyone's is familiar with this. They know what to do. Now you have the weekend to, kind of look at some of this material and make notes. Say, geez, I don't understand this. So maybe you could ask questions about the various practice tests, and I can kind of show you how to do them. Now, if you start a practice test and you don't really know how to answer the problem, before you start it, you need to look at it and know how to proceed. If you can't do that, you're not ready for the test yet. So go back into the sections until you get comfortable that you can just look at a problem and say, oh, I know how to start this. Then you're ready for the test. If you look at a problem in chapter 10, 11, and 12, and then the first thing is you got to go to look at the book, look at your notes, look at some of the exercises, examples in the book, then you're not ready for it. You have to be able to look at that problem and without using any other resources, know exactly where to begin. And that's what I would say. Instead of jumping into the problems in the practice test, look at them. Just glance over them and say, oh, that's this sort of problem. How do I solve it? And be ready in your mind to look at that and just know how to begin. Because many students study incorrectly. They look at a practice test and they look at a problem and they say, okay, I know that's something. And then they go back into their notes or they go back into the textbook and then, oh, that's how I do it. But on test day, you don't have that option. So what happens? You're not trained to do it that way. So your brain freezes up because then you're used to looking for how to begin and you don't know where to start. And sometimes it eventually comes to you, but it's hard. You want to be able to look at any problem in those chapter tests and say, oh, I know what is being asked of me and I know how to begin. And if you're at that point, then take the test and check and see if your answers are correct. If you still have to look up on how to do it, you're not anywhere near ready to take the test. A lot of students don't understand that, but that's the best way to study at this point. Look at them first. Don't jump into doing them. Do I really know what to do? What is my strategy for solving that problem? So, any other questions?
Excuse me, Professor?
Mm-hmm.
I joined late. I was just wondering if you called on me to check the homework.
Yes, I did.
Oh, can I show you it now?
Yeah, do that. So, for everyone else, I want you to everyone stay safe, smile, wake up, and have a good weekend. Yes, there. Okay, I see it. Got it. Have a good weekend. Stay safe. If you can get your vaccine, do it so we can get all to a safe spot. And even though younger people are not affected as terribly, there's some younger people that have gotten some terrible reactions from it. Now, it's killed some of them, but also even people that didn't kill, they got long-term effects, permanent effects on their lungs, their hearts, and we still don't know what this virus is doing. So you don't want to be in that group. Maybe it's only 1 in 100, or 1 in 1,000, but you don't want to be that unlucky 1 in 100 or 1 in 1,000. I mean, the vaccine itself, some people have a negative reaction.